Welcome, 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 everyone. This is our last of our four a Café size, and so it's always kind of the start of the end of summer for us. Before we get started, I want to be sure to thank, we have a lot of important donors and sponsors in the audience, and I want to take a moment to just say a big thank you to all of you. We are largely funded by the federal government through grants and contracts, also contracts with industry, but about 15 to 20% of our annual budget every year comes from philanthropy, and we could not do the work we do without it. Grants simply just don't cover everything. So a big thank you for that. We always want to say a big thank you to H.M. Payson, which is a Maine financial firm, because they sponsor these Café size every year, and they've been doing it for a long time. So a big thank you to them. And I'm going to save the rest of my thank yous until at the end of the talk. So today it is my pleasure to introduce Catherine Mitchell, Dr. Kath Mitchell. Kath is from Scotland. She received a master's degree in physics and mathematics and then went on to get a PhD in physics. So she likes light, fluffy science. She came to Bigelow in 2015, and she came to work as a postdoc with Barney Balch. Barney was the gentleman who gave the talk, the first of the four of this series on the history of Bigelow. In 2019, we promoted her to research scientist. And actually, our former vice president of research, who is now the director of ocean science at Bigelow, director of ocean sciences at the National Science Foundation in DC, Jim McManus is in the back of the audience. And Jim was one of the three of us that really sat down and were thinking, you know, we think this young woman has incredible potential. We're going to promote her to research scientist. Not very many of our postdocs get promoted, so it's a really big deal. And I remember thinking at the time, let's just see what this lady can do. And she knocked it out of the park. Between 2019 and 2021, she brought in 4 large grants. That's huge. 4 large grants that early in her career is incredible, for over $2.5 million. And she has just been an incredible person in our community. She's a lovely human being. She's a wonderful mentor. There are still way too few young women going into science and going into mathematics and physics. And so having a role model like Kath is really important for young women to see themselves as a physicist or a mathematician. She is one of our most productive scientists, and in fact, she's so productive, she's now currently producing a human being on top of all the great science. So with that, I want to introduce Catherine Mitchell.
Thanks, Debbie, for that great introduction. Debbie said I like light and fluffy science. I do like light science, maybe not so fluffy. So thank you, everyone, for coming today. As Debbie said, I'm someone who studied physics and maths, but I ended up in an oceanography lab. And today I'm going to be talking to you about one area where these two worlds meet, and that's satellite oceanography. In the first talk of this series, Barney Balch talked about the lab's guiding principles, and the final one was understanding that we stand on the shoulders of giants. And I wanted to start with this principle and our lab's co-founders, Charlie and Clarice Yenge. Charlie and Clarice were both giants for founding the lab, but also in their respective scientific fields. And while Nicole Poulton, who gave the second talk in the series, talked about Clarice's role in flow cytometry, I get to talk to you today about satellite oceanography and the role that Charlie, as well as a lot of others at Bigelow, have played in this area. And Charlie really was a giant in the world of satellite oceanography, so I'm really happy to be able to tell you this story. And so we're going to go back to about a year and a half before the lab was founded, December 1972. And this is one of the first colour photographs that was taken of the Earth by a human. It was on the final Apollo mission to the moon. And it's known as the Blue Marble. It's apparently one of the most widely known photographs on Earth. And it's called a blue marble because the Earth looked like a small blue marble hanging in the darkness in outer space. And that blue colour is because of the ocean. And so today, the type of satellite oceanography we're talking about is really about measuring the colour of the ocean using satellites. And the ocean isn't the same blue everywhere like it kind of looks like in this picture. If we zoom in onto two sides of the Gulf of Maine, Cape Cod and the Bay of Fundy, we can see there's a lot of different shades there, different shades of blues and greens and yellows and browns. Particularly as you're getting closer to land, those brown colours are appearing. And those colours are telling us that there are different things in the water. That green water is where there are algae or phytoplankton, these single cells that live in the ocean. They're the base of the marine food web. And they're like the plants on the land. And they're green like the plants on the land because they have a pigment in them that makes them look green. And then when there's a lot of them in the ocean, the water tends to look a bit greener in colour. And then you have the browns from the mud and the silts and the sands or dissolved plant material that's in the water. And so the real question, though, is how do we measure this colour? And our eyes and brains, or most people's eyes and brains, are pretty good at this. We don't really think about it. You look at something, like my dress, and it's blue, and you just kind of know that. But how do we design an instrument that will do this? So here we have a rainbow that shows all the different colours that we can typically see. And so the first ocean colour satellite that was launched was the Coastal Zone Colour Scanner, CZCS. And it was kind of a proof of concept satellite. It was a test to see if we could build an instrument and put it into space and measure ocean colour. And what we really were interested in measuring was that algae, so like how green that water was. And so what CZCS was designed to do was basically measure 3 different shades of green, and then it also measured a little bit of how red the ocean was. And that red was really important for something that we call the atmospheric correction. So if you imagine you have a satellite sitting up in outer space and you have light that comes out of the ocean, it has to get all the way through the atmosphere before the satellite can see it. And so what we need to do is remove that atmospheric signal. And that's what that red colour is used for. And so fast forward this mission, I'm going to talk a lot more about this mission through this half of the talk, but spoiler, it was a success, and we've had a bunch of other ocean colour satellites come along since then. And CWIFS was kind of the next one that came along, and the big advance with it was rather than just measuring these 3 shades of green, we suddenly were measuring, how many is that? 5 shades of green and blue, and then a couple more out in the red to help with this atmospheric correction. Next satellite came along was MODIS. We have an additional red colour in there as well. And then VEERS was kind of one of the more recent ones launched, and it actually had slightly less, but still very useful satellite and lots of good information. And I just want to point out that these are the NASA and NOAA ocean colour satellites. Other space agencies around the world have launched some too, and they're pretty similar to these. But the big challenge for all of us, no matter the satellite, is once we've measured the colour, can we relate it to the stuff that's in the water? That's really what we kind of want to do. For example, if the water is green, that means there must be algae in it. Can we say how much algae there is depending on how green the water is? And to do that, what we have to do is we have to be out on the ocean in a ship, measuring ocean colour along with whatever we're interested in, like how much algae there is, at the same time that a satellite goes overhead. And this allows us to be able to check that the satellites are seeing what we think they are seeing. And this is something that, again, I'll talk about a bit later, but that I've done quite a bit of work in. So I'm going to take us now on a bit of a journey timeline through the history of ocean colour and satellite oceanography. is going to start actually way back in the late 1800s, because this was the first time the colour of the ocean was quantified in some way. And that was with this thing that we now know as the Farrell-Uly ocean colour scale, after the two scientists. And this is a very plastic, modern version of that scale. Back in the 1800s, it was chemical dyes, different chemical dyes, ranging from the blue that you see in the top left through to the brown. And each one was just given a number, 1 for blue and 21 for that brown. And you would compare your ocean sample with that chemical dye, and the ocean was just, colour was just given one number. And so clearly we're still using that plastic version of that scale today, because it's a really good way for us to be able to connect back to some of those historic measurements that were made. And again, I'll come back to that later too. And so fast forward a little bit to the early 1900s, and this was around the time that Henry Bigelow, the lab's namesake, was sailing around on his schooner in the Gulf of Maine, making a bunch of oceanographic measurements, including some of those Farrell-Uly colour scale measurements. So we have measurements of colour in the Gulf of Maine from over 100 years ago. Now we're going to fast forward again up until the 1950s. And this is really around the time that ocean colour, or what we call ocean optics, really started to kick off as a science. And a lot of this was during the 50s and 60s, led by a Danish scientist, Jarlov, who, like me, was a physicist and mathematician. And what we like to do is write a lot of equations down that describe the world around us. And that's what Jarlov did. He wrote down a lot of equations to figure out how light interacted with stuff in the water and made a particular colour. And so he was kind of pioneering this ocean colour theory, or ocean optics. But while he was working on all this math, people were actually starting to make much more advanced measurements of ocean colour than these Farrell-Uly type numbers that had been made. They were making measurements much more like I was talking about earlier for the satellites at particular different colours. And this was an international effort, especially by the late 60s, but one of the first people to do some of this work was Charlie Yench. And what he was doing, these are some of his early publications from the early 60s, papers that he wrote, some of the science that he was working on. And what he was really doing was measuring how algae, the phytoplankton, in the water influenced its colour. And this bottom paper is actually the first paper that discussed how the perceived colour of the ocean might vary due to the differing amounts of algae that were in the water. So that's a really big deal. It became a really big deal because what he's saying here is, yes, we can see there's these different colours and it's related to how much algae there is in the water. And that piece of insight was really important for moving the field forward. So we have some people doing a lot of math, we have some people doing a lot of experiments and observations around the world at the same time, and this was pretty exciting. But starting in the late 50s and 1960s, something else was happening in the world of science and engineering that captured the attention of people across the globe. I'm not going to ask if anyone knows. 1957, maybe some of you know what happened, was when Sputnik was launched. The first satellite launched by humans was launched by the Soviet Union. And hot off the tails of the launch of Sputnik was the founding of something went wrong. Yes, was the founding of NASA. And while much of the public's attention of NASA's activities were focused on the space race and the moon landings, there was something else that was going on. And that was the Nimbus program. So in the early 1960s, this program was kind of going on. It was a research platform for trying out new instruments on satellites in space. And so people were beginning to think about oceanography from space. And in 1964, in particular, this conference, small meeting was held, Oceanography from Space, down in Woods Hole. And it was convened by Gifford Ewing, who was an aircraft pilot. He worked at NASA, and he went on to become a long-term member of Bigelow's Board of Trustees in its early years. And I don't know the exact details here, but I assume Gifford Ewing and Charlie connected at this meeting or earlier if they hadn't before, because a few years later, they flew an aircraft carrying an ocean color instrument out over the Gulf of Maine. And what they saw were some changes as they flew over different patches of water. And further flights and more data led to the first paper suggesting that ocean color and how it changes could be analysed remotely. So all the work that Charlie had been doing before was taking samples and measuring colour in the lab, whereas here they're on an aircraft and they're seeing those colour changes. And so if you piece all this oceanography along with all this space race stuff together, natural conclusion is it possible to detect ocean colour from space? And we could build an instrument and launch it on the Nimbus platform. And that's kind of what happened. In 1973, so this was really a fast timeline from when these ideas started being talked about to when this satellite was first conceived and then later launched. So in 1973, the Coastal Zone Colour Scanner was approved and the design started. And a member of the science team was Charlie Yench. And so starting with CZCS and all the ocean colour satellites we have today, we have these things we call science teams. And in these days, they advised a bit on the design, like which colours of light were important to measure, but also they are some of the first people to look at the data and then interpret it, turn that colour into something like how much algae there is. And so there was a lot of work to be done before the satellite was launched, so they could be ready for when they first started receiving data. But if anyone knows their Bigelow history, because launching a brand new proof of concept satellite wasn't quite enough, in 1974, this boat pulled up to the dock in West Boothbay Harbour, and Charlie and Clarice started Bigelow Laboratory for Ocean Sciences. So the 70s was an exciting time here and in the world of ocean colour science. And so by 1978, so only 5 years after they said, okay, let's do this thing, CZCS was launched. It was designed to be a one-year mission, but actually lasted about 8 years, which was kind of remarkable. So we got a lot of interesting data from it. And the first couple of years was some frantic testing by the science team, and by 1980 they were convinced that the Coastal Zone Colour Scanner worked. It detected patches of ocean colour, and they could estimate how much algae was in the water. And I want to show you here one of the first images of the Gulf of Maine from space, showing how much algae there is. This was June of 1979. And so chlorophyll A is that pigment that makes algae and grass and trees and leaves all green. And so the way the ocean colour satellite works is it's detecting how much of that chlorophyll A there is. And so areas in this map where it's greener, it means there's more algae, and areas where it's blue means there's less algae. And all that white stuff is clouds. Because what we're dealing with is colour and light, we can't see through clouds, and the satellites can't see through the clouds either. This gives you an idea of how cloudy this region is, that if you launch a satellite in October, it might not be until the following June that you actually get a fully clear satellite image. And so I'm really used to looking at these types of images. Some of you may have seen images that look like this, but to people in the late 1980s, this was something completely new and in some ways mind-blowing. And there's a lot of detail here that people hadn't really anticipated. And the ocean wasn't just uniform, and satellite images really revealed that. I have a couple of quotes or comments here from people around that time. The first is from Charlie Yench. He said George's Bank, which is this area out here, he'd done a lot of work out there, so he knew that area pretty well. He said it looked as he expected it to, but along the coast, we see a lot more variability. Like up here, it's much darker green, and down here, it's much lighter green. And if you look closely, you see this changes, these shades of green change as you go along the coast. These are known as like squirts and jets. And that was a surprise. They expected it to be quite uniform along the coast. The other thing that surprised him were seeing some spinning eddies generated by the Gulf Stream. And so the Gulf Stream is, sorry about my crude arrow, the current that comes up the eastern seaboard and goes across the Atlantic. But spinning off of it are these big rotating bodies of water. And you can see a couple kind of eking up here underneath the clouds. And we knew that these were physical features that existed, but what the ocean colour imagery revealed was that their colour was different. And so that meant there was something different about the algae that was within these eddies as well. And these popped out really clearly in these images. And the other quote I want to give is from Janet Campbell, who's another scientist at Bigelow for about a decade. And that's this one. When one first deals with remotely sensed data, one is overwhelmed by the wealth of data in one image. Each image is a single point in a time series. The challenge is to discover which features persist and which features are transient. The true usefulness of remote sensing data is yet to be realized. And if you note the date that she said this was 1986, which was 8 years after CZCS was launched. It was also the year that CZCS died. So it kind of gives you an idea of how revolutionary this was, that even after the full duration of that image, we're still talking about how useful this data could be. So while there was some great progress made from some of the CZCS observations, in some respects, science advances were kind of slow compared to what they are now, not from lack of interest or effort, but from computation. So at the time, computers weren't like they are today, and storing and sharing all the data from the satellite was a challenge. And in 1986, Bigelow received funding to establish the Remote Sensing Image Analysis Facility. It was run by Janet Campbell and managed by Jean Garside. And at this point, all the satellite data was stored on magnetic tapes, and it was housed in a facility at Bigelow. I've heard there was just a room full of tapes. I don't know how true that was. And at the Bigelow facility, they had a lot of the tapes that covered the Gulf of Maine, plus some extras that Charlie had acquired through his work on the CZCS science team. And so apparently, they hired a high school student to go through these tapes, note down the location of the exact area each image covered and the date, and make a small database so that when someone came along later and said, I want to see the Gulf of Maine on this particular day, they could just pull out the one tape that they needed. And so Bigelow was one of 10 sites in the US to house the CZCS satellite data. Then, the next moment in our timeline is 1988. So, some of you may have come to all the previous talks in this series, and I know they all started with photographs of my colleagues in 1974, and I didn't start there because I wasn't alive in 1974, but I was born in 1988, and just as the field of ocean optics was taking off. And so, where did things go from here? The first ocean colour satellite mission is over. There's me, ready, young budding scientist, ready to go. And luckily for me, things didn't stop with CZCS. So from 1997 and still ongoing today, we've had a continuous ocean colour satellite record that covers the whole globe. And here I'm just going to highlight the satellites that I mentioned earlier in my talk, the ones that were kind of managed and designed and developed by NASA or NOAA. So this started with CWIFS in 1997, and it stopped working around 2010, and then the MODIS instrument was launched on the Terra platform in 1999, and it's actually still going. All these satellite missions I'm going to mention after this are still in the sky today, in space today, I should say. And so then a second MODIS instrument was launched on a different satellite platform, and then in 2012 was the first time a VIIRS instrument was launched. And so all of these are measuring ocean colour around the whole globe. In the early 2020s, another VIIRS instrument was launched on a different platform, and then earlier this year, PACE, a brand new ocean colour satellite, was launched. And I'll talk about PACE a bit more in the second half of my talk. And what's common about all these instruments was they all look at about a square kilometre of the ocean, and, well, they look at the whole ocean, but they can't see anything smaller than a square kilometre. But you get a daily image of the full planet, which is pretty incredible when you think about it. And Bigelow has been involved in all of these satellite missions in one way or another, mostly through the science and validation teams. And so the science team, like Charlie was involved in for CZCS, he was involved in the CWIFS one, as was Barney Balch. Barney was also involved in the MODIS science team, as was Janet Campbell. And then more recently, I became involved in the MODIS and VIIRS science teams. And then the other teams that both I and Nicole Poulton at Bigelow are currently involved in is the validation team for PACE. And so the validation team is responsible for being out on the water and making those measurements of ocean colour at the same time that the satellite goes overhead, like I talked about earlier with that great cartoon of a ship and a satellite drawn. Okay, so I just want to point out a couple more things on this line. 2015. So 1998, I was born. In 2015, that was the year that I came to Maine and to Bigelow. And this is a picture of me and a colleague at the time, Amy Wyeth, doing one of those validation trips that was being run by Barney at that point, out on the Gulf of Maine. And so where has 20 years of satellite ocean colour data got us? It's got us to this animation, which is known as the global biosphere, showing how much biology, how much life is on the planet, on the land, and in the oceans. And so in the oceans, that's algae we're looking at. And the dark purples and blues are where there's not a lot of algae, and where they're yellow and red is where there is a lot more algae. And what you'll see as this ticks on is some seasonal patterns, some consistent features. And I just want you to imagine if we'd only been able to use ships during this time. All we'd have is a few lines across this planet each year, if we were lucky. And instead, we get this kind of image every day of the whole planet. So it's really revolutionised our view of the ocean. And as this ticks on, I just want to tell a quick story. On 2007, it was the 10-year anniversary of the launch of CWIFS, and Paula Bontempi, who was the NASA Ocean Biology and Biogeochemistry Program Manager at the time, was going to give a science update. And the NASA Public Affairs Office had never heard of CWIFS. So what they did was they compared the number of academic publications and papers about CWIFS to the number from the Hubble Space Telescope. And it was the same. And the NASA Public Affairs Office was completely blown away because nobody had ever heard of CWIFS. And so just wanted to highlight it because outer space seems to grab interest much more than our planet back then, and that might still be true today. So while all of this data makes these really cool animations and videos, I wanted to highlight some of the science that's been possible because of satellite ocean colour. The first one on the list here is the global distribution of algae and how it changes each day, so kind of what we were just looking at. It's important because algae are the base of the marine food web, supporting all ocean life. So it's good to know how that changes in time and space. And then we've also seen connections between the ocean physics and the biology. Like I talked about those eddies spinning off of the Gulf Stream, and we were able to connect like that physical eddy feature with something about the biology of what's going on in there. Because we get this data so regularly, it's used for monitoring and tracking events such as harmful algal blooms or oil spills. We've also been able to estimate some forms of carbon in the surface oceans and how those vary in time and space. And these data are all used in large-scale climate and ecosystem models as well, which are useful for predicting the future. And so, end this part of the talk by talking about one area of science done at Bigelow in support of oceanography, which my research is kind of following on from. And that is the Gulf of Maine North Atlantic Time Series. So it started by Barney, who's here, in 1998. Well, Charlie had actually done some crossings and some transects, but it started continually by Barney in 1998. And it was funded by NASA for satellite validation. So again, us being on the water, measuring ocean color on sunny days when the satellites could see us. And we had this mobile lab here at the time, and we were really measuring ocean color, but also focusing on phytoplankton at the base of the marine food web. And I recently took over running this program for the newest ocean color satellite, PACE. And here's just a picture of the transect that we do, this white line with the big NATS label. All the other lines and dashes and labels are currents in the Gulf of Maine. Don't need to look at those. And so I chose this picture like a couple of weeks ago because this was the last picture of Barney and Bruce, who worked with Barney for a long time before they retired. Last picture of them doing a trip on NATS. But that was actually until last Friday when Bruce joined our team in my place because I couldn't go on the boat. We did a test trip for these cruises moving forward where we were using Bigelow's new research vessel. And sounds like it was a great success. So it's really exciting. Still have to look at all the data. And I'm very grateful for Bruce stepping up to do that trip for me. And so I just want to highlight one change quickly that we've seen over the time of NATS, and that comes back to this Farrell-Uli scale and that ocean color measurement. And like I said, Henry Bigelow was making these measurements back in the early 1900s, and we've been making them. And so something Barney did was compare Henry Bigelow's measurements to ours, and what he found was the Gulf of Maine's really got yellower over time and over that century. And we think that's mostly because of increased precipitation, and so more runoff of plant material from the land, and when that mixes with water, it makes it a kind of yellower color. And so I want to end this part of the talk coming back to the timeline. That was one event in 2012. It's actually two events. 2012, September was the year that Charlie Jensch passed away, and less than a month later was the Ocean Optics Conference, which is a big conference in our field. That year happened to be in Glasgow in Scotland, a 5-minute walk from where I was in graduate school. I was a first-year graduate student, so I got to go, which was good for me. And there's a tradition at that conference where giants of the field are remembered. And at that point in my career, I didn't know too much about Charlie's exact work or what he'd done, but I remember both Barney and Paula Bontempi standing up and speaking about Charlie. And I don't remember what either of them said, but I remember thinking, wow, he really did do a lot for this community. And fast forward another 12 years, a few twists of fate, and here I am standing here and talking about him and what's been done at Bigelow in support of satellite oceanography. And so with that, I'll stop and take some questions. So we're going to continue with the second half of the talk, be much shorter. So the theme for our 50th anniversary this year is the next 50, celebrating the past, solving for the future. And so I'm going to take a look ahead and talk about the potential for this technology and area of research over the next 50 years. And for this part of the talk, I want to go back to that slide that I started was early in the first half of the talk, where I highlighted the different colours that the ocean colour satellites can measure. Well, this gets to Barbara's question. PACE is this new satellite that was launched in 2024, and the colours it can measure, kind of all of the colours. It's going to be measuring just over 100 different colours. And if you just think about how different that is, if you were given 7 crayons to draw the world around you, and then someone actually just gave you 100 crayons, like think about how much more detail you would be able to draw with all those different colours. And so, what do we think we can actually do with all those colours? And so here, I have a little bit of a graph I'm going to walk us through. What we're looking at is ocean colour when there's lots of algae in the water. And so, what we're looking at, this line here, is something we would see from one of the existing satellites that we had pre-PACE. And so the dots are like those 7 colours that satellite would measure. And along here, this bottom part of the graph, it's kind of showing you that colour. So like over here, these are the blues and greens, and then these dots are those 2 red colours. And then as we go up, it tells us like how much of that colour did we measure. And so here, there's lots of green because there's lots of algae, and not so much blue and not so much red. So the new PACE satellite would see something a bit more like this, a much smoother line that goes between all these dots. And so we're still hitting all those dots, so, but in between, you can see it's not like these kind of straight lines. We have these kind of curves and bends. There's a lot more detail happening in there. And like the question that talked about different phytoplankton that have different colours, all these algae are absorbing light slightly differently, and they have these slightly different colours. So if you, for example, here is a second line that I've drawn that would represent a slightly different type of algae than the green line was. And the thing to notice here is this second line that I added on, it goes through the same dots as before. But out here, it's kind of a bit different. But if we just had that existing satellite and we're only looking at those dots, these 2 lines would look the same. But with PACE, because we get all this detail, we're able to pull apart some of these differences between the different lines because of the different algae that's in the water. And so this is really exciting. It's a pretty major advance going from there are some algae there to there are these groups of different types of algae there. And we can start to ask a completely different set of questions, like when does one group dominate versus another group? When does one transition from one type to a different type? So it's kind of really exciting to see where this will go as we get more and more data from PACE. And I just wanted to show you an image, one of PACE's first images from February 28th of this year. And on the left-hand side, we have something that's a bit more photograph-like. It just uses 3 colours. It was made using 3 colours, a red and a green and a blue colour. And then out here, sorry, this is the left. On the right, we have this chlorophyll A image. So again, how much of the algae is there? How green is that water? And this is like what these older existing satellites would see. That's all they could see was how much algae there was. But then this big bit in the middle is something that we can only get from PACE. And this is 2 different groups of phytoplankton. And it's really showing an example of what we were just talking about. We're going past identifying that the algae are there to identifying these 2 different groups and how much there are of these 2 different groups. And this is just one example of the type of thing that we could do with PACE. And with this technology advance, it makes me think back to the early days of CZCS, when people's eyes were opened by those first images. And that's kind of how I feel right now with PACE. We've got this really exciting new instrument up there, and I believe there's a lot we're going to learn from it, and we're really just knocking on the door. And I want to come back to that quote of Janet Campbell's from 1986 and change the last sentence slightly, because this sums up exactly how I feel about PACE, that the true usefulness of PACE data is yet to be realised. There's so much we're going to be able to do, and we don't even really know what that is yet. But what's even more exciting is things don't end with PACE. So Glimmer is a new proposed up-and-coming mission that will have an ocean colour instrument very similar to PACE, but it's on a geostationary satellite. And so PACE and all the other satellites I've talked about up until now, they go around the poles of the Earth. They're a polar orbiter. So that's how they're able to see the whole of the planet. Whereas a geostationary satellite sits in one place and always looks at the same point on the Earth. And what the big advantage of that is, it's always looking at the same place, so you see how things are changing all the time. Whereas with the other instruments, we only saw the planet once a day. So with Glimmer, we'll be able to see how things change within the course of a day, which is another pretty exciting thing. And Glimmer is designed to focus on the Gulf of Mexico. It will look there 6 times a day, but it'll look up both the east and west coast of the US about 3 times a day. That's the current plan. And so this is due to be launched in a few years, and this allows us to ask some slightly different questions, like how are these groups of phytoplankton changing over the course of the day, rather than just getting this one single snapshot. And then the next technology I want to talk about that could be pretty exciting is having a dedicated ocean LiDAR. And so what's a LiDAR? And so it's like a radar, but with light. And so you shine a light into the ocean, and it would go down and it would bounce off stuff that's in the water and be reflected back out. And it gets to the question that asked about how deep can we see. And so the ocean colour satellites I've been talking about are looking kind of in that surface layer we talk about. But with an ocean LiDAR, it would be able to get much deeper and see what's going on deeper down, where, to be honest, often much more phytoplankton are hanging out. And so LiDAR systems have been used for looking at the atmosphere for a long time, satellite LiDAR systems. And oceanographers have been guinea pigging off of those to look at the oceans. But a dedicated ocean LiDAR would be a major advance because it would be designed to actually go deep into the ocean. The atmospheric ones, while they go in a little bit, they don't go in as much as oceanographers would like them to do. And so this again would be another one of these big eye-opening moments. And this is something that is talked about in the community, and momentum is growing, so I wouldn't be surprised if in the next 50 years we're talking about all we've learned from LiDAR. And we, Barney and me, have done a bit of work with some colleagues that use a LiDAR in the Gulf of Maine. So here it is on the Endeavour. I was not on this trip. But our colleagues down at Old Dominion University built a seagoing LiDAR system that they can use on a ship, and they joined us on a few of our NAT strips cruises. And we learned some cool things about that data. So who knows, maybe watch this space in the future. And so far, I've been talking about new technologies and where those could take us. But I wanted to end with talking about an exciting new science advance, something I'm particularly excited about. And that is when the ocean colour community started this journey, this ocean optics journey. We were thinking about phytoplankton. And over time, we thought about some other things too, like sediments or dissolved materials. But those were always phytoplankton sized or smaller. And something we at the Marine Optics Lab at Bigelow Laboratory have been thinking about and working with colleagues back in Scotland on our zooplankton. And so these are the next step up the food chain from the algae. And the question that we were interested in is, if there is enough of them in the ocean, surface ocean, could we see a colour change that is detectable from satellite? And the answer to that question is yes, we can. And so this image here, we're looking at the yellow areas are where we're seeing a lot of these zooplankton, and the blue, dark blue areas are where we're not really seeing any. And but the thing we need to think about is we need to be able to design and build instruments that are capable of measuring the optical properties of these larger sized particles, not really particles, but larger sized things, so that we can really validate the observations that we're seeing in these satellite images, because that's a major challenge right now. All the instruments that we've designed to date to look at optical properties of stuff in water were focused on phytoplankton-sized things, so they just don't see the zooplankton, which makes our lives particularly challenging, but also very exciting. And so this is a pretty new area of research, and I believe this is another one of those moments where we're opening the door to a whole bunch of new work, and that's a really exciting place to be. And I'm happy to be doing it at Bigelow, not just because of the history we have in satellite oceanography, but because I've got some great colleagues in the building that know a lot about zooplankton, because I honestly don't really know much about them, other than they sometimes make the ocean look a little bit red, and I can see that from space. And so before I take questions, I wanted to give the last word to Jim Acker, who's a scientist at NASA Goddard, and he wrote a book on the history of NASA's ocean color satellite missions, which I relied on fairly heavily for putting this talk together. So it felt right to give him the last word, and this comes from his dedication at the start of the book, which is to Charlie Yench, Andre Morel, and Dennis Clark, without whom the science of ocean colour measurements from space would have been nearly impossible to accomplish. So I'll take questions now.
Okay. We made a good bet with her, didn't we? So this is the last of our 4 Café size, and I wanted to just take a moment to thank the people that have made this possible. First of all, the Opera House. We could not have done this if we didn't have a place to do it this year. Thank you, thank you, thank you to the Opera House. I wanted to acknowledge, we have a number of board members in the room. We have Marion, can board members stand up, because I don't want to miss anybody. We have Marion Howard, we have Judy Kildow, our mighty board chair in the back, Wen Wolf, Elizabeth Bishop. I mean, we are not an enormous organization, and so we try to recruit people with expertise that can help advise us, and so we can be as successful as possible and bring their thoughts and their creativity and what does Bill Burgess' story say? Their time, talent, and treasure, and they do, and we're so grateful. We have a number of Bigelow staff here. Our communications staff, we've got Joe Ebersino down here and done a great job. Our advancement staff, we have Jessica, I see Dana Wilson in the back. Jennifer Cutchell is over, our mighty leader of our advancement team, and Michael Villarello. Sorry, there's this very bright light in front of me. So they're fantastic. Thank you so much. We have our communication team. We have Colin and we have Leah. They are also in the back. And so when you hear stories written in the press, they've had some really huge. Is Stephen here? He's not here this week. Stephen Profizer, who's the head of that group. We've had a lot of success in the communication area lately. If you watch Nova, there is a 3-part Nova series, and we were big chunks of the first 2. It's called Sea Change. David Fields is like a superstar in it. It's almost like an actor portraying an oceanographer. So check out that. Ben Twining, our Vice President for Education, just had an opinion piece on iron fertilization in the ocean in the Boston Globe. So they're just doing a fantastic job pushing out a lot of information. And then we have Abby, our mighty, she's like does everything. She is, will answer the phone, she will give you a tour, she's fantastic. And then we have a whole bunch of our staff here. I see Nicole Polton, I see Barney Balch, who is technically retired, but actually, I've been impressed at how seldom I've seen you at the lab. I was like, nothing's going to change, but that's because he has a big garden. So we'll see how he does in winter, successfully retiring. Bruce Bowler, who stepped in for Kath, he's in the audience watching. Anyways, there's so many wonderful people at the lab, and I'm so grateful that you all turned out to hear about the science that they're doing. We really are a global lab. We have people in oceans all around the world, and they're doing incredible science, and we're so grateful to all of you for supporting us in that work. We couldn't do it without you. Thank you. Oh, here's Captain Dave Drapeau. I should just stop because I keep seeing new people. But so many great people from Bigelow are here tonight as well. So thank you all. I hope to see you next summer. We will be in our new Education and Innovation Center at the campus in a beautiful forum, multi-use forum. So you won't have to sit around the bend. You can actually see the slides from anywhere. I'm always so impressed on how many people still showed up and stuck with us, even though they couldn't see a thing. We're very, very grateful. We will be putting these talks online, so you will be able to see them online. I hope you have a great winter if I don't see you between now and next year, and thank you so much for supporting the lab. We're so grateful.